Data structures are the unsung heroes of the digital age. They are the silent architects that shape the way we store, access, and manipulate data. Without them, the digital world as we know it would be chaotic and inefficient. They are the fundamental building blocks upon which we organize and manage the vast amounts of data that permeate our world. From the simplest of tasks like storing a contact in your phone to the most complex operations like running a global search engine, data structures are at the heart of it all. Imagine a library with millions of books. This library is a treasure trove of knowledge, but without a system to organize these books, it would be nearly impossible to find the information you need. You would spend hours, if not days, searching for a single book. Without a well-defined system of shelves, catalogs, and indexing, finding a specific book would be an impossible task. The same principle applies to data in computers. Without data structures, our digital information would be a jumbled mess, making it incredibly difficult to retrieve and use. Data structures provide this essential organization in the realm of computers. They allow us to store data in a way that makes it easy to access and manipulate. Whether it's a simple list of items or a complex database, data structures are the key to efficient data management. They dictate how data is stored, accessed, and manipulated. For example, an array allows us to store a collection of items in a specific order, while a hash table provides a way to quickly look up values based on a key. Each data structure has its own strengths and weaknesses, making it suitable for different types of tasks. Just as a library uses shelves to arrange books, computers use data structures to arrange data in memory. This organization is crucial for ensuring that data can be accessed quickly and efficiently. Without it, even the most powerful computers would struggle to perform basic tasks. This structured approach is crucial for efficient data processing. When data is organized properly, it can be processed much faster, leading to quicker results and more efficient use of resources. This is especially important in today's world, where the amount of data we generate is growing exponentially. Different tasks demand different approaches to organization. For example, a search engine needs to quickly find relevant web pages from billions of options, while a social media platform needs to efficiently store and retrieve user data. Each of these tasks requires a different type of data structure to be performed effectively. Similarly, different types of data and computational problems call for different data structures. Choosing the right data structure for a given task can greatly impact the performance and efficiency of a program. It's like choosing the right tool for a job. The better the fit, the better the result. Choosing the right data structure can mean the difference between an elegant, efficient solution and a cumbersome, time-consuming one. A well-chosen data structure can make a program run faster and use less memory, while a poorly chosen one can lead to slow performance and high resource consumption. Understanding data structures is akin to understanding the grammar of a language. Just as grammar provides the rules for constructing meaningful sentences, data structures provide the rules for organizing and manipulating data. Without this understanding, it would be difficult to write effective programs. Once you grasp the fundamental rules and structures, you can begin to construct complex and meaningful programs. This knowledge opens up a world of possibilities, allowing you to tackle a wide range of computational problems with confidence and efficiency. High-performance computing, or HPC, pushes the boundaries of computation. It represents the pinnacle of technological advancement, where the limits of processing power are constantly being tested and expanded. HPC systems are designed to perform complex calculations at unprecedented speeds, enabling breakthroughs in various fields. It tackles complex problems that demand immense processing power. These problems range from climate modeling and genomic research to financial simulations and artificial intelligence. The ability to process vast amounts of data quickly and accurately is crucial for making significant advancements in these areas. These problems often involve analyzing massive datasets, simulating intricate systems, or running complex algorithms. For instance, predicting weather patterns involves processing data from numerous sources, including satellites, weather stations, and ocean buoys. This data must be analyzed in real time to provide accurate forecasts. In this realm of speed and efficiency, data structures play a pivotal role. They are the backbone of efficient data processing, enabling quick access and manipulation of data. The choice of data structure can make or break the performance of an application, especially in high-performance computing environments. The right data structure can significantly accelerate computations. For example, Using a hash table for data retrieval can reduce the time complexity from linear to constant time, making the process exponentially faster. This is particularly important when dealing with large data sets where every millisecond counts. Conversely, an inefficient data structure can lead to sluggish performance and wasted resources. Imagine trying to search through a poorly organized database. The time and computational power required would be enormous, leading to delays and increased costs. Imagine searching for a single star in a detailed map of the Milky Way galaxy. The sheer number of stars and the complexity of their positions make this a daunting task. Without an efficient way to organize and search through the data, finding that one star would be nearly impossible. Using a simple list of stars would require you to examine each star individually. This linear search method is not only time-consuming but also highly inefficient, especially when dealing with millions or even billions of stars. This would be an incredibly time-consuming task. The inefficiency of such a method becomes glaringly obvious when you consider the scale of data involved in high-performance computing tasks. Time is a critical factor, and any delay can have significant repercussions. However, if the stars were organized into a hierarchical structure based on their location in the galaxy, finding your target star would be much faster. Hierarchical data structures such as trees or graphs allow for quicker searches and more efficient data management. This is the power of choosing the right data structure for the task at hand. By optimizing data organization and retrieval methods, we can achieve remarkable improvements in speed and efficiency, paving the way for new discoveries and innovations in high-performance computing. One of the most fundamental data structures is the array. Imagine a row of numbered boxes, each capable of holding a single piece of data. This is the essence of an array, a contiguous block of memory locations, each associated with a unique index. Arrays excel at providing fast and direct access to specific elements. If you know the index of the data you're looking for, retrieving it from an array is lightning fast. This makes arrays ideal for storing and processing large sequences of data, such as sensor readings, stock prices, or simulation results. However, arrays have limitations. Their fixed size means that once you've created an array, you can't easily grow or shrink it. Inserting or deleting elements in the middle of an array can also be computationally expensive, as it requires shifting all subsequent elements. Linked lists, flexibility and dynamic growth. Unlike arrays, linked lists offer flexibility in size and structure. A linked list is like a chain of nodes, with each node containing a data element and a pointer to the next node in the sequence. This dynamic structure allows linked lists to grow or shrink easily. New nodes can be inserted or existing nodes can be removed without the need for costly data shifting. This makes linked lists well suited for applications where the amount of data is unknown or changes frequently. However, linked lists have their drawbacks. Unlike arrays, which provide direct access to elements based on their index, accessing a specific element in a linked list requires traversing the list from the beginning. This can be inefficient for tasks that require frequent access to arbitrary elements. Hash tables, rapid data retrieval. In this section, we delve into the fascinating world of hash tables, a fundamental data structure that plays a crucial role in computer science and software engineering. Hash tables are the masters of data retrieval. They are designed to provide rapid access to data based on a unique key, making them incredibly efficient for various applications. They are designed to provide rapid access to data based on a unique key. This unique key is used to generate an index through a process known as hashing, which allows for quick data retrieval. Imagine a dictionary where you can instantly look up the definition of a word. Instead of flipping through pages, you jump directly to the word you need. Hash tables work in a similar way, providing instant access to data. Hash tables work in a similar way. They use a hash function to map each key to a specific index in an array, ensuring that data can be retrieved quickly and efficiently. They use a hash function to map each key to a specific index in an array. This hash function is crucial as it determines how well the hash table performs in terms of speed and efficiency. This allows for near constant time access to data regardless of the size of the hash table. The efficiency of hash tables makes them ideal for scenarios where quick data retrieval is essential. Hash tables are widely used in databases, caches, and symbol tables, where fast lookups are essential. Their ability to provide quick access to data makes them indispensable in these areas. However, hash tables are not without their limitations. One of the main challenges is handling collisions, which occur when different keys map to the same index. Collisions, where different keys map to the same index, can occur and need to be handled efficiently. Various techniques, such as chaining and open addressing, are used to resolve these collisions. Additionally, hash tables do not maintain the order of inserted elements, which can be a drawback for certain applications. Despite these limitations, the benefits of hash tables in terms of speed and efficiency make them a vital tool in the world of data structures. If you learned something new, like the video, share your thoughts in comment section, and don't forget to subscribe the channel for more related videos.